Okay, cool. Let me go ahead and share my screen. Can you guys see that okay? I'm going to assume yes. All right. So this is Lab 3. You're going to make an array-based stack in Q. Um, so we'll basically go over kind of what the stack's behavior is, and then we'll go over what the queue's behavior is, and then I'll go in a little bit more detail about these things. So for a stack, both a stack and a queue are data structures. They're their own separate data structure. So when you guys do this for the lab, it's two different parts, and you'll be making two different data structures. They're not really like put together or anything. Um, so for the stack itself, you're going to have two functionalities associated with it. It's going to be the push and the pop. Um, so you can kind of think of this, the best way is like a stack of plates. So if you were to have a stack of plates, unless you had like your most favorite plate you wanted to use, typically you're not going to pull from the middle of this stack, right? You're going to just pop it off the top. And I think, Mark, can you go ahead and mute yourself? I think there's some music going on. Um, so it's like a stack of plates where you're basically going to pop off the top. Um, and when you go to put plates on, you're actually going to put them on top of the stack, right? So here you can see a diagram where we push the first piece of data, and we push the second, then the third, and the fourth. And then when we actually want to remove this data, you're actually going to pop it off the top. So we need to access the last thing that was put in. So it goes 6, 5, 4, 3, and 2. This is an example of LIFO, which stands for last in, first out. So the last thing in is going to be the first thing out, right? We put things in by pushing, and we take things out through popping. If you want kind of a concrete example of where these stacks data structures come in handy, one is when we refer to the stack and the heap in memory that you guys have been learning about for the past week. That stack is based off of the stack data structure. That's why it's called a stack. And basically what you'll find on that stack is you push the functions and the data onto that stack, and which with each function call, we're actually popping the function call off when we exit from the function, and we're pushing it onto the stack when we're entering the function. So for instance, if we look at this diagram right here, one could be like our main function. So when our main function opens up, that gets pushed onto the stack. And then if we call a function within main, that would be the second one pushed onto the stack. And if there's a function called within that function, it would be the third one that was pushed onto the stack. And then when we return from these functions are going to then pop off of the stack. And that's where we get the behavior of like losing all of our memory, where if you pass something in by value, it will basically get lost because it's going to get destroyed when it's popped off the stack. You won't really have to worry about that kind of memory relation for this lab. I was just giving you a kind of concrete example of where these stacks are used. Any questions on the stack? Okay. So there's going to be a queue as well that you're going to make. This one is a little bit more like a line than the stack is. So you can basically picture this like a line at Disney or like a line in the cafeteria, where it's going to follow the principle of FIFO, which is first in, first out, meaning the first person that has been in that line is the first person to get served. So we can see you have the front and the back. Putting something into the queue is called in queue. That's the vocabulary associated with this. And when we take something out, we're dequeuing it. And that's so this is similar to push, and this is similar to pop, but where those pushes and pops are happening are a little bit different. So the queue is a little bit makes a little bit more sense to like what us as humans are used to. Although I think the stack is a little bit easier to program logically, and you'll see why in a little bit. But that's the one that you guys end up starting with. Part one is the stack, and part two is the queue. Okay, so let me go ahead and kind of draw out how this will look in code. I'll go over the other stuff in a second. I'm just trying to find a blank spot to draw this. So like we talked about, this is ABS and ABQ, which stands for array-based stack and array-based queue. So these things are data structures. And this might be the first time that you guys are getting experience with like building a data structure or building some kind of tool for a program. So I've had a couple students already ask me, like, what is this program even doing? Like, I understand I'm making a stack, but like, what's the purpose of it? Um, and the purpose of building the stack is to just make a data structure that somebody else is able to use within their program. So, for instance, you guys have been using a vector for probably a couple of your labs now, and you guys are probably pretty familiar with vectors themselves. So, a couple developers actually had to make that vector as a data structure. They had to develop code to make that vector functional. Um, and that's exactly what you guys are doing here. You're basically making a tool, a data structure to allow someone else to use it. So if you take a look at the main code associated with this lab, it's basically Fox just using your tool and just doing a couple pushes and pops. It's pretty trivial, but the reality is someone could take your stack and actually implement it in their own program. And when you guys go further on in your CS or computer engineering career, you'll start seeing more data structures and start understanding a little bit the ideas behind them. Um, so for this one specifically, for the stack and the queue, you need to make this using an array as your backing data structure. So you're using a primitive data structure, an array, to actually make this data structure operational. And this is going to be done with dynamic memory. So you guys have learned about dynamic memory now, and now you get to use it. So I'll go ahead and annotate this a little bit on what this is going to look like. So let's go ahead, draw this. So we'll start with the stack for now. So within your constructor, you're going to end up with making a size of only one. But let's say that we've already made a couple spots already in the dynamic memory for the array. So let's say we have a size of 5 associated with this. So this is just an array. This is going to be for the stack. So when you actually push items onto the stack, you're basically just going to push them into the most zeroth index, right? So if we're pushing like 3, for instance, and then we push 5, and then we push 7, and then like 10, that's basically going to just take the standard of putting things in an array, where you're basically going to put it in the next most available index, right? You guys are going to realize you're going to have a current size associated with your array, which is basically going to keep track of how big your array is and also where the next available space is. So that current size variable, or size variable, whatever you choose to call it, kind of has like it helps you in like 2 places, right? It helps you keep track of the size, and then it helps you keep track of where to insert the next element. So the pushing happens by just putting it into the next available element, and your pop functionality is going to be used by actually just returning what's inside of the rightmost index, which for your stack becomes your topmost index, right? So if you kind of invert this thing vertically by rotating it like 90 degrees counterclockwise, that basically takes the shape of your stack, right? Where you can basically pop the 10 off and think of the 10 as the top of your stack. And then you can zero this out if you want to. But what you'll find is if you just kind of move where your current size is located, like either here or here, depending on how you're indexing, when you go to do your push, you can just push in a new element at that old location, and it's basically just going to overwrite what was ever there. So if we push back like a 9, it would just overwrite that 10. Meaning you don't necessarily have to zero it out, and a lot of students are under the impression they have to like delete that value. But that's not really a thing in C++. You can't just like delete the value. You can like zero it out or clear it, but you can't really like delete it. And if you try to actually use the delete keyword, that would be like deleting heap memory, and that would run into a couple issues there. So really, you just kind of move where your variable is pointing, and then you can just like override it from there. Any questions on how the array is used within a stack? Okay. So the next one we'll do is the queue. So let's go ahead and pick a different color. So this is going to be a queue. It's going to use the same exact thing, an array, just as the stack, but our functionality becomes a little bit different. And the main thing is how we need to pop. So you technically have a couple options with how you want to do this. Even with the stack, you have a couple options. I just think the one I showed is the easiest one. Uh, but I would say the easiest thing to do with the queue is to use the same push functionality, which is where you can just push it right from the 0th index. So we can push all these elements in here. It was like a 10 originally. And that's just basically your push functionality. But the difference here is with the queue, you have to take what was first in, right? So this guy right here was the first in, right? So we have to remove him first. So if we go ahead and do that here, and then let's say we pop another element, what you're going to find, and hopefully it's kind of obvious, is basically now you're just wasting space. So if we push a few more elements in here, what you're going to see is we're out of room in our array, but we're not technically out of room in our data structure. So technically, as far as our user is concerned, he still has 2 more spots for the queue. But your backing array thinks we only have or that we have no spots, right? Because your current size would have been pointing here, and we're like out of room. So to remedy this, basically the best way is to just shift your elements down to the left after every pop. So when you pop this 0th element here, you're basically just going to shift everything down to the left. And that will keep the rightmost as clear as your queue actually is. Meaning what's blank in your array is accurate to what is blank in your queue. Another option, which I don't really recommend, but just letting you know that there's one out there, is to make some kind of circular buffer where instead of shifting everything down, like once you get to the last location, you start filling up from the left-hand side, and you fill this with 12 and then 14, and then it's clear. And then if you pop, you have to keep track of where you're popping from. But I think that is a little bit more complicated than just shifting elements down, because now you need to keep track of both the end and the beginning of your array, and where you're actually popping from. But if this seems super easy to you and you want to challenge yourself, feel free to do the circular buffer method. My personal recommendation is just going to be to shift stuff down. Questions on the queue? Okay. So the next thing I'll go ahead and talk about for this lab is resizing. So let me go ahead and clear. We'll just leave this up for now. So one thing that you might be thinking of is, well, if we make this a dynamic array, it's still just going to be a specific size within that one allocation, right? So what happens if the user comes in and basically fills up all their space inside of your dynamically allocated array, what they believe is a stack from their perspective? We don't want to really limit the user on how much they can put in the stack, because we don't know how much they're going to need. They might only need to do it for 5 elements, or they might need it for 500. And we don't want to allocate, 500 blocks off the bat, and waste all that space if they're only going to use even half of it, right? And we don't want to limit to them to only 100 if they're going to need more than that. So this is the whole purpose of dynamic arrays and dynamic memory, where we can basically change the size on the fly. Now, here's the thing. We can't actually change the size of this specific array. So what you actually have to do is you have to make a new dynamic array that is either bigger or smaller, determining on the conditions, and then copy over each element manually within a for loop or something. So let's first go look at the resizing rules. And then I'll go ahead and actually draw this out like I've been doing, and show you kind of what that resizing would look like. So in the spec itself, if you have it pulled up or just look at it later, there is a section here right after he kind of talks about the description. I guess it's still part of the description, but they go over what the resizing rules should be. So you're given a scale factor for this lab, which is going to be 2.0f, which is just a float, right? Basically, it's a scale factor of 2. So anytime you attempt to push or enqueue, which is putting stuff into your data structure, if it's full, like if it's full up, then you will need to resize the current capacity to the current capacity times the scale factor. Because the scale factor is 2 in this case, you're basically doubling the size of your data structure. So this is a push, but it could also be an NQ. Well, actually, this is technically push because you're putting it on top of the stack, but the same principle applies to NQing, where basically if we realize that we're full because of the push, we're going to then double the size here. And that's based off of the 2.0 scaling factor. Obviously, if the scale factor was 3, then we would triple the size of it, or 4, we'd quadruple the size of it. For the popping, it's a little bit different. So when you pop or DQ, it's based on a percentage full. So the current size over the max capacity, that's just the percentage of how full your data structure is. If that becomes strictly less, so just meaning less than, not less than or equal to, then 1 over the scale factor, then you're going to resize the storage to the current capacity over the scale factor. So basically, if it is less than a half in this case, so if it's less than half full, you're basically going to scale it down to the current capacity, which is what you have, over the scale factor. So you're basically dividing your current capacity in half. So this 2.0 makes it a pretty simple thing to kind of remember. You're basically doubling it if it's full, and you're cutting it in half if it's less than half full. And what this basically allows us to do is to kind of like change our data structure based off the user's needs. This one I think makes sense to everybody. Basically, if they need more memory, give them new memory, right? Here, the problem is if we just keep letting them use this data structure where they have a bunch of this memory kind of being wasted, we're just wasting memory on the user's machine, and that's never really good, right? We basically want to just use as much memory as we need. And that's kind of why the scale factor it exists, right? So if you did some playing around with this and realized the scale factor needed to be 3, you'd make it 3, right? Again, for this lab, it's 2, so just keep it as 2. But those are the kinds of things that you can change around to kind of alter the way your data structure behaves. And it's also better than just like increasing by 1 each time, because that's a little bit of a tedious process, and you're making the computer do a little bit more work than it needs to, as opposed to just doubling it once and then being done with it until you might need to double it again. So and this is where he talks about the resizing. You can't just change the array, you actually have to create a new one. So definitely follow this right here. And this is basically kind of the script I'll go over down here while I draw it out. So that is definitely not the behavior I wanted. I may have lost all my beautiful drawings. Okay, we're just going to restart. Okay, so if we go ahead and just draw the stack again, I'll just do the stack because I only really need one thing for this resizing purpose. But let's say we have this stack and it's all filled up, right? So we need to make a new size. Basically, inside of your push function, or if you make a new function for resizing itself, which is totally fair to do, what you'll need to do is the steps he has above, where you basically create a new array of double the size. So let's go ahead and do that. I find drawing these things out makes it a little bit easier to kind of to picture in your head. A lot of times if students come to me for help, I'll either draw it out or have them draw it out, so it's a little bit more clear. So what this has 5 elements, so we need 10, 2, 3, 4, 5, 6, 7, 8, 9, 10. A little small at the end. And then basically what you're going to do is manually copy these things over inside of like a for loop. And that's basically just moving everything down into the array. And then you have choices for these other 5 elements. You can just leave them how they are, which is just garbage memory, or you can zero them out. It's totally up to you. Zeroing them out might be helpful for the user because they can see if they start moving into like 0 index, or you as the developer starts moving into stuff that is 0 indexed. not zero index, but has 0 as the element, you can be like, I'm accessing bad data. Or you just leave it as garbage data. And personally, I find that a little bit more clear because it's an insane number or an insane negative number that you haven't entered in your system. And you're like, okay, this isn't, I'm going too far past the actual data in this stack or queue. But like I said, you guys have options. Once all of this is copied over, so I won't draw them all out, but you're going to have like a 3 here and then a 5 here, and then all of these the same here. And then you're basically going to delete this old array. And that's important because if you don't delete this old dynamic array, you're going to end up with memory leak issues. And then whatever pointer you had that was pointing to this array, you're now going to point to this array. But remember what we went over last week is you're going to want to change, you're going to want to delete what you're pointing to if you don't need it anymore before you actually move where that array is pointing to. So any questions on the resizing or anything I've gone over? Cool. Let's go ahead and nuke this. So one last thing to talk about on the lab, and then we can kind of move on from this, is the templating. So you guys, I believe, just learned about templates yesterday. So you're basically going to template this data structure out. And if you remember, the purpose of templates are so that we don't have to make the same program for multiple different data types. And this should make sense for a data structure. If we're storing some type of data, we don't want the user to have to like basically pick like, oh, I want an int stack or I want a string stack or a character stack. They're just going to give us that input when we actually make the class. And yeah, Joshua, we're going to be making a template class. And really all it is you just put that template and then the less than greater than symbols and then type name T before your class, and then you're good to go. One thing I forgot to mention is you're going to be doing all of this in a header class, like a header file. You don't have a source file a part of this. So if you define all of your functions within your header file, you don't have to type the like template like type name T above each of the function calls because you don't need that scope resolution operator. Because you're already inside of the class. Basically, where you typically declare your function in a class, you're just going to define them right in that same location. And that makes it a little bit easier. But yeah, you're going to be making a template class. And you can see that with the pop and the peak functions here, where the T is like the data type you're returning, because we don't know what data type that's going to be until the user picks it right in the beginning. When it's like actually constructing the object. And I think that's pretty much it. We have the BigThree you guys are making for both of these, which I'll go over after I'm done with this. You have your normal default constructor and regular constructor. And then you have, for the stack specifically, you have the push function, you have the pop function. And I didn't talk about the peak, but all the peak is doing is just returning that top value without actually popping it. So you don't actually have to remove it during the peak. It's just the user being able to see what's at the top of the stack. Something to note out of all of this is there isn't any way to have like random access. We can't just randomly access any element in the stack or the queue. And that's on purpose. That's how these data structures are defined. You basically can only access what's at the top of the stack or what's at the front of the queue. If you wanted something with random access, you would just basically build a different data structure. So it might seem limiting. It might seem kind of a stupid data structure that you can only access what's at the top or the front. But there are certain applications that actually might need that behavior, and that's the behavior that is actually wanted from the user. Cool. And then, yeah, just the same thing for the queue. It's just the DQ and the NQ, and it has a peak function. So you're going to see a lot of similarities between these two when you're building them, and then one or two core differences, like shifting elements down when you do the pop versus the NQ, or when you do the NQ versus the pop where you don't have to shift anything. So any questions about the whole lab before I move on?
So that example you went through quickly where you like created a new array, moved the elements over, and then deleted the old array. That's what a deep copy is, right?
Yes, that would be considered deep copy. Yep. Um,
Okay.
it that specifically doesn't happen within a copy constructor or a copy assignment operator, but that is something that would be considered a deep copy, because you have to go through and manually copy over everything. Yep. Cool. Any other questions? All right. Let's go ahead and open this up. Okay. Can you guys? I don't think you can see my screen anymore because I think I only shared. Can you guys still see this?
Yeah, we can see it.
Okay. Well, my green line disappeared, so I can't tell what you see anymore. Okay. All right. So for those of you who have been coming to labs and whatnot, I'm basically just building on top of the student class that I did in the first week when I went over classes. Um, and all we're going to do today is just make a destructor, a copy constructor, and a copy assignment operator, and kind of go over the anatomy of those and like the syntax and what they kind of provide for us as programmers in the C++ language. I'm sure Fox has gone over this a bit, but in semesters past, it's questions that I've got a lot. It just basically the difference between all three and when to use one over the other. So hopefully I can preemptively answer all those questions, and then it'll be a little bit easier for you guys going forward. So let's go ahead and set this up. Got a bunch of stuff from today's earlier lab. And do this. Don't care about that. Okay. Cool. So I think the way I'll do this, I think it worked well last lab, is the first thing I'll go over is the copy constructor. And then I'm going to go over the destructor, and then I'll go over the copy assignment operator. And I'll basically touch on like the difference between the copy constructor and the copy assignment operator, because I think there's a lot of confusion when it comes to those. It seems like they're doing the same thing, and for the most part they are, but there's a couple little key differences. So let's go ahead and take a look at main first, so we can see what this program's actually doing. So it's really just these lines right here that is actually dealing with the copy constructor. So the first thing we do is we make a new student called Trevor. So we're just constructing a new student object with the default constructor. And then we go ahead and set his ID number to 10. And I should probably back up and show you guys that there is a variable in here called ID number, and that is a pointer. And the reason that we're setting this as a pointer is because it's going to deal with dynamic memory, and to set a variable equal to something in dynamic memory, it needs to be a pointer, right? So that's kind of the data type back here. And I just made it public so I can access it without using a getter or a setter. So inside of main itself, I basically access Trevor's ID number and I set it to 10. And in his constructor, which I meant to show you guys, that ID number in the default constructor is going to be set to a new integer. So that actually has a like new value associated with it. Let's see. Okay. Cool. So that's going to be like memory on the heap that we're setting this equal to. And then we go ahead and do a copy constructor, and it's going to be student Brad is equal to Trevor. So we're basically trying to copy over Trevor's elements and have Brad have those same elements. So I get a lot of questions on whether, like, how do I know if this is a copy constructor or a copy assignment operator? And that's an excellent question. So I'll bring you guys up to here, where I think it'll make a little bit more sense if we kind of just look at this in terms of like primitives. There's no actual like constructors called on primitives as far as I know, but I think looking at this kind of independent of classes will make the concept make sense. So on line 25, we just make a new x integer and set it equal to 10. And then we are actually making a new y integer and setting it to x. This is basically the similarity of where we call a copy constructor. The reason is because we're actually initializing a new variable. We're actually making a new variable, something that hasn't existed before. So you can kind of think of this as the construction of the object, right? It's a copy constructor, meaning it's actually making something. Um, on the other side of this, there is the copy assignment operator. So we'll make a new variable z and set it to 7. And then when we do y is equal to z, this is what a copy assignment operator would look like. There's no constructor in the type of like title of what this is because nothing's actually being made. Y and z both already exist. We're just basically trying to copy z stuff into y stuff. Um, so that's basically the core difference between the copy instructor and the copy assignment operator as far as like viewing it from a usage standpoint. Um, so on line 34, this would be considered a copy constructor because Brad hasn't existed yet, and we're actually creating a new instance of a student class. We're making a new student object. So hopefully that makes sense. So now let's go ahead and see what the copy constructor is actually doing. So we go over here and look at this copy constructor. Let's take a look first at the arguments that are being passed in. So this is going to be a const student reference. So let's kind of break down what those things are. So const basically means whatever we're passing in, we can't edit, which is good. That's what we want because what's being passed in is the old student, the thing that we're copying from. And there's no reason that us as the developers should be able to like edit that. If we're just trying to copy something, we shouldn't have access to that the thing we're trying to copy stuff to like actually manipulate it, right? We just want to copy it. So that's why we protect it with the const and kind of make it like a read only element. Um, Student is because it's a student class. Hopefully that's kind of clear that we're copying a student object, so it needs to be a student object, right? And then the last thing is just that it's a reference, and this is so that we can actually have the student itself and not just a copy of the student. Um, and then I've personally called it old student, meaning the thing we're copying from, because this makes the most sense in my head, and I think it's made sense to people I've explained it for in the past. Old student being the student on the right hand side, the student that already exists that we're copying from. If you go look up these copy instructors online, and some of you may already have, you'll see a lot of people do RHS, and Fox may do this. I'm not super sure. But all this stands for is right hand side. So right hand side of the equation. So if you look at the line that actually calls this function, Trevor is the right hand side, which is what's actually like this variable that's actually being passed in. So like I said, I just call it old student or old whatever thing I'm copying from to differentiate it from the new thing that I'm actually creating. So that's kind of what all this is. So let's go ahead and see the types of copying we can do. So this example here is a shallow copy. And a shallow copy basically means it's a member to member copy. We are going to just copy over one variable into another variable, right? Typically, this is perfectly fine. And if you don't define your own copy constructor, this is what the compiler is going to implicitly do. This is what it's going to implicitly make for you. The issue is if we start dealing with dynamic memory. Once we start dealing with dynamic memory, we most likely are going to have to implement the BigThree. And I'll kind of show you why that is here in a second. But basically, this shallow copy isn't going to work with dynamic memory. And the main reason is that we're only copying over the pointer into another pointer. And basically, we set one pointer equal to another. They're both going to point to the same location. Which, if we're doing that with the ID number, essentially what that means is Trevor and Brad are going to have the exact same ID number. So it's not just going to be a copy; it's going to be the exact same like place in memory. They're both going to point to the same thing. So that means later on, if we go ahead and change Brad's ID number, Trevor's ID number is going to change. And I'll go ahead and compile this and show you that right now. But what you see here is I'm printing out Trevor and Brad's ID number. Both of these right here should be 10 in the beginning because we've just copied that over. But once I change Brad's, Trevor is still going to be 10, or Trevor's now going to change to 30, which is it's what we don't want, right? So that's the behavior we get. hopefully you guys recognize like why this is an issue and why we wouldn't want something like this. If we're making copy of an object, there's no reason they should come out of the copy sharing the same exact stuff, right? And even if this was an array, like an array of stuff, they'd now share the same array of stuff. So if you're like editing that array, it's going to edit it for both objects. And again, this all stems from the fact that if you set pointers equal to each other, they're going to point to the same location. So hopefully what I'm about to say doesn't throw you guys off too much, but really the reason that the dynamic memory is an issue with these shallow copies stems from it being an issue with pointers themselves, where when you set pointers equal to each other, they're pointing to the same spot. So that's kind of like why dynamic memory ends up being an issue here, because you always have to use pointers with dynamic memory. But if you get down to the nitty gritty of it, it's really the pointers causing the issue themselves. So hopefully that gives you a little bit more insight of like what's really going on in the background. So let's go ahead and like fix this issue, right? So what we can do here is comment this out, because we don't actually want this happening. And let me just actually comment these out too. And what we can do is a deep copy, which if you'll see, these three lines right here in the beginning, like all three of these are the same exact here. And that's fine. These are technically still considered a shallow copy, but that's okay because they aren't pointers. They're not pointing to dynamic memory. They're just stack variables. So it's actually going to copy it over into a different instance of a stack variable. Those new stack variables already exist. It's the dynamic memory that we actually have to fix and deal with. So how do we fix this? We're going to go ahead and set this ID number, which means the new object we're creating, Brad. We're going to make a new integer on the heap for his ID number. So we already have like Trevor's ID number on the heap. Now we're making a new integer like on the heap. And what we're going to do is dereference both of those spots, and we're going to copy it over into that spot. So we're going to do old student.id number, and we're going to dereference that whole thing because it's a pointer. And this is basically going to return the value at that location, which is 10. And then we're going to set that to the dereference value of the new object's ID number. And that now that 10 is going to be properly copied over, and they're going to be two different locations. So if we go ahead and run this again, the thing at the beginning was the same. Both of them ended up being 10, which is expected behavior. We've copied that 10 over. But then once we've changed Brad's ID number on line 44 to 30, Trevor's ID number remained untouched, as it should, because it's a completely different location. So this is kind of how you fix those issues for dynamic memory. If this was an array, like what you're dealing with in the stacks and stuff, right here is where you'd have to like manually copy over everything within a for loop. So if this wasn't just like one integer, which is a pretty trivial application, usually you wouldn't just like put a new integer on the heap like this. You would just leave that as a stack variable. But it's for demonstration purposes. If this was an array, then you would have to go through and manually copy everything over after you've made a new array. So any questions on the copy constructor?
So the copy constructor is essentially just like a constructor with a parameter, and the parameter is the like another object of the class that you want to copy over, right?
Exactly. Yep. Exactly. Cool. Any other questions? All right, cool. So I'll go do the destructor next. And the reason I want to do this next is because it stems from a problem that we saw when our copy constructor was incorrect. So we take a step back and see that, well, I don't need to comment this out. Basically, when I had this shallow copy going on and I ran this, we got this like double free detected. And this was stemming from the fact that in our destructor, we're deleting the ID number, right? So let's kind of talk about what the destructor is supposed to do. And then I'll talk about why this happened. So in a destructor, it's the destructor's job to go through and basically destroy your object and clean up anything that the object may have left. And by anything, we're typically talking about dynamic memory. So for the both of these objects, they've made a new integer on the heap, and it is the destructor's responsibility to go in and delete that memory. It's possible that other functions within your application actually already have deleted some memory, but basically your destructor is like the last catch to basically delete anything that still remains. So this one's pretty simple. We're just basically deleting the ID number, and that's all that needs to be in the destructor. Um, and so it's going to take care of like deleting the memory of this like new int that we made. So if we take this delete out, we can go ahead and run what we've done before, which is valgrind. And I'll just prove to you guys that there are like some memory leaks here. So we're leaking 8 bytes in 2 blocks, which hopefully makes sense to you guys because in one of our constructors, we made a new integer for Trevor. And in the other copy constructor, we made a new integer for Brad. And we haven't cleaned up any of those. So that's 2 integers, 4 bytes an integer, 8 bytes total on the machine that's left. If we add this delete in here, we can see that this is cleared up now. And we're basically have 0 bytes and 0 blocks leaked now. So let's talk about why this was an issue for the double free. Basically, when we had the shallow copy in here, and let's go ahead and run this and then do main. You can see we get this like double free, like it basically has crashed, right? It's aborted, the core is dumped, and it's telling me a double free has occurred. And if we kind of think of why this is, it's because when we did this copy constructor, we pointed these pointers to the same spot. And once the destructor is called at the end of this program, it first goes in and deletes the memory associated with Trevor. So it deletes its ID number. And then it goes and tries to do the same thing with Brad. But the problem is these 2 ID numbers were pointing to the same location. So it's already deleted that location, and then it goes in and it tries to delete the same location when it does the destructor for Brad, which ends up being a double free, and it'll crash your program because it doesn't know how to delete something that's already been deleted. So I basically kind of shown this to you guys because it's not out of the realm of possibility that you guys end up doing this in your applications, and I want to give you guys some insight on why that might be occurring. So it could be an issue with your copy constructor not being set up correctly. It could be your destructor not being set up correctly, and it could do with your destructor trying to delete something that your application has already deleted. So always just keep this stuff in the back of your head. If you see that double free, the first thing you think is like, oh, okay, like I'm deleting memory that's already deleted. Let me go figure out what that thing is. Dynamic memory, new deletes, they can all be kind of hard because this program won't end and tell you like, oh, on line 10 you're deleting memory that's already been deleted. You kind of have to go play a little detective game and figure it out. So let's go ahead and comment this in. Any questions about the destructor?
So an object is deleted when it falls out of scope, right?
Right. Yep.
So would there be any other instances where it'd be deleted?
What do you mean by that? Like any other times when the object is deleted?
Yeah, other than falling out of scope.
I don't like you can call the destructor explicitly. I'm pretty sure. Like you, well, I don't. Let's actually try it. Because I don't know. Like if we do, yeah, I don't know if you can actually. There might be a way. I don't think this is going to make any sense. Yeah, I don't think because the constructor is just called by like giving the name. Let me look that up real quick. Other than it being possible that maybe you can call a destructor explicitly, I think it's just going to be when it falls out of scope or the whole application terminates. Which the whole application terminating is basically main just falling out of scope, if that makes sense. I don't know if that kind of answered your question or not.
Yeah, I think so. I was just curious if like there would be a time where we would have to, but it doesn't sound like it. So.
Gotcha. Yeah, it's basically whenever it's done running. Let me see if there's a way to explicitly call it because I feel like there might be, but I just don't know the syntax. Okay, so it looks like it might just be this. Um, okay, so let's kind of see what this does because I don't know. Okay, so it looks like what happened kind of makes sense. So let me run this and make sure that we're in a good working state. Um, okay, so we get another double free when we add this explicitly in, which hopefully what you guys have learned up to this point kind of makes sense because now we're explicitly calling the destructor on line 35, but then when the program terminates, it's going to implicitly call it again. And then we end up with another double free because it's now trying to delete the situation in Brad's twice. I think one thing you can do is actually wrap this and do if this. Um, let's see what this does. My assumption here is that this will return false if like the actual object doesn't exist. Um, but I could be wrong. Yep, I was wrong. I think I don't know. This probably won't make sense either. I'm just trying stuff now at this point. Yeah, I don't think you can set an object to a null pointer. Okay, we tried. There might be some kind of way to hack around this where you can like do some kind of check in your destructor that basically is checking like if your object is like actually alive, then don't try to delete the memory. But I don't know what that syntax would look like. So yeah, you can go and play around with it. If I figure out a way, I can message you guys about it. But I don't know off the top of my head. But there might be something out there that exists. So good questions. Okay, let's go get rid of this. Okay, so the last thing to talk about is the copy assignment operator, which is quicker because the same issues are the same with the copy constructor. But let's talk about when like a copy assignment operator would actually be done. So if we go ahead and let's see how to do this, where we have a student Brad separately and then a student Robert separately constructed, and then we change Robert's ID number to 20. And then we set Brad equal to Robert. And then let's go ahead and change that to printing out Robert stuff instead. Um, so here, if we remember what I went over up here, basically Brad and Robert already exist at this point on line 38. So there is no constructor being called. It's just the copy assignment operator. Um, so these two objects already exist, and we're just copying one into the other. So the same ideas are here, where there's a shallow copy and there's a deep copy. So let's go ahead and see what that shallow copy would look like. It's exact same syntax, exact same stuff going on as the one that was up here. And what you're going to see is it's pretty much the exact same issue. Where you change one and you're changing both, right? It's the same stuff with the heap. So we fix this in the same way, but then there's one other spin on it where because you're creating a new integer, one already exists in memory for Robert, like right, like one or for Brad, for both of them, there's already memory that exists. So you want to delete the original ID number, and then you want to make a new integer on the heap for the new pointer, and then basically then you can set it. If you didn't delete the old ID number when you called line 68, you are basically going to you're basically going to end up pointing to sorry, lost my train of thought. If you don't delete this, you're basically going to end up with a memory leak, right? Because you're just basically moving your pointer to where it's pointing to. And so if we go ahead and run this, we won't get any memory leaks, and you're going to see that the expected behavior is what we wanted, where we changed Brad's ID number to 30. One note on this is you could also get away with just dereferencing, because now you're just copying. Now that the memory already exists in two different locations, you can just dereference one and copy it into the other. Where you're going to need something like the deleting the ID number and making a whole new one is if you're dealing with arrays, right? For this one, you're going to have to make a whole new array, especially if it's a different size. You could get away with, I guess, copying each element over individually, assuming that the arrays are the exact same size. But like if Robert's array is bigger than Brad's, then you won't be able to do that. And I guess also you're going to figure out like your like how you work around that, where you're trying to copy over something that's like bigger than the other. But these are the kind of the two options that you have here, where you either delete it and make a whole new one, or you basically just dereference them and set it equal to the other. So the copy assignment operator is pretty much the same logic as a copy constructor. So most of what you type in a copy constructor, you can just do down here with a couple different tweaks depending on what exists in memory at this point. Something I didn't go over is like the syntax of the function like definition. So starting on the left-hand side, where the return type now is a student reference. And basically this should make sense because we actually need to return something now because it's not a constructor. And then this right here is basically just like operator, like overloading, I believe, where it's the operator, you're overloading this equal symbol here. So you can tell this equal symbol, like what it's actually doing, like what the definition is. And then this is the exact same parameters as the copy constructor. It's const, so we can't change it. It's student because that's the type of object we're dealing with. And it's a reference so that we can actually not manipulate, but so that we can actually get that exact object and not a copy of that object. Yeah. Any questions about any of this? It doesn't have to be just the copy assignment, but anything you guys got? Okay, cool. That's pretty much all I had for you guys. Hopefully this was helpful. Good luck on your quiz if you haven't taken it yet, and good luck on anything you guys have this week. And good luck on the lab. Come see me if you need help. Yeah, no problem, guys. You have a good one.